Well, it's great to actually be here. Good morning. Thanks. I understand that there was a little fun yesterday, but I'm glad everything worked out and appreciate Hemant stepping into the breach. I am, for those who don't know me, and I see a ton of new faces here, which is awesome. I'm Chuck Lukaszewski. I'm in the CTO team at Aruba Networks. We're the networking division of Hewlett-Packard Enterprise. And what I want to do is tell you about probably the most important, exciting thing to happen to Wi-Fi from a spectrum perspective in a little over 20 years, and kind of give you a sense of what's coming in terms of new channels in different countries, but also kind of give you a little peek behind the curtain about how spectrum gets allocated, because all of us have been taking advantage, and really we take for granted, we don't mean to, but we do. We've been taking advantage of work that a group of people did about 25 years ago to get the spectrum we have now in 5 gigahertz in particular. We're doing that again for really the next 20 years, if you will, to make sure that we can continue to grow the industry and keep up. So before we get into that, I have a little announcement to make here, since I know there's a ton of CWNP folks in the room. This is kind of a soft announcement of a program I'm excited to help with here. So the Aruba Training Department is partnering with CWNP, and we're doing what we call a scholarship program, where for the next 6 months, starting April 1st, anyone that tests for and certifies their ACMP, we will throw in a CWNA training e-learning program and test voucher. And we're really excited to work with CWNP because the curriculum obviously is great. I know there were boot camps running last week, and you've heard me speak for years about it. We're very excited. They've refreshed the curriculum, particularly the CWNA curriculum, and it's just great to be able to sort of give back to the community. So I'm really thrilled to be able to do this. There'll be more data about the program, and I'm happy to talk to you offline afterwards. This is being run through the Aruba Training organization. So the agenda for this talk is just some level set about the 6 gigahertz band generally, and then a little bit about who's there now, because there's no unallocated spectrum in the world, especially in the mid band. Talk to you a little bit about the process, both in the U.S. and in Europe, that we're going through, and how the sausage gets made. Then we're going to go kind of sort of deep into a study that was delivered by the Wi-Fi industry last year that is kind of a mandatory part of this kind of a process. And then finally, we'll wrap up by talking about what's called AFC, the automatic frequency coordination. This is a phrase you're all going to get very familiar with as we move ahead with the band, because it's going to be necessary. This will be like the DFS for 6 gigahertz. In the sense that DFS protects us in 5 gigahertz from the key incumbent, which is radar systems. So in 6 gigahertz, we have different incumbents, and AFC will be the technique that is used to protect that. So let's start with the kind of the current state of play. So this is a 5 gigahertz situation in a number of different selected countries. And the basic message, and you all know this, you work with this spectrum every day, and you're really on the front lines of it. But the 5 gig build out is basically, for all intents and purposes, over. And I have an asterisk on it because spectrum is never really over, but there is at least one significant question mark. But the plan had been that the middle of the band, so the 5350 to 5470 chunk, the big kind of red area in the middle with the cross out through it, that was going to be kind of the next place that we could go. And in particular, that was going to light up 2 more 80s. And then the Uni 4 band on the high end, which you may be reading about in the news about, it's a intelligent transportation band. That's another 75 megahertz. And the notion basically was if all of that got lit up, we would have potentially 9 contiguous 80 megahertz channels, which really gives us a ton to work with, right? But some things kind of didn't pan out as expected. In particular, there's one There's one national security-related incumbent use in the Uni 2B band, and despite a lot of work by all parties, it's just not possible to address that particular incumbent. So that band is off the table globally basically indefinitely. And then the Uni 4 proceeding has been largely stalled. It's been going on for years, and there's been some recent activity in it, but even if that were to happen, it doesn't really move the needle, right, in terms of the number of 80s. The work that's left to do in 5 gigahertz is really what we call harmonization, which is just kind of getting the rules lined up between as many countries as possible. And clearly there's a lot of opportunity for that here, but it's not going to get us a lot more channels, which is not, the congestion issues is what we face as network architects. So why do we need a new band? So the first reason is spectrum is the foundation of everything we do, right? Whether you're, I know we have, end users in the room, we have integrators, we have vendors in the room, technology companies, all of us effectively take this thing for granted. The cellular industry has to go buy spectrum, right, every 10 years or so when a new G comes out. But we got it sort of allocated to us again, as I said, and it didn't happen by accident. It was a lot of work, and there was no Wi-Fi when that work got done back in before 2000. And so, now you would think it is easier, but of course, the demand for spectrum has only increased in the meantime, and so there's a lot of contention. We also want to keep pace with the 5G in the cellular industry, so it's crucial. They have, depending on the country, a good chunk of the 3 gigahertz band has basically been allocated, designated for what's called IMT, which is basically cellular. We want to make sure Wi-Fi, if you caught the new Cisco VNI, mobile VNI is out about 2 days ago. And it continues to be the story of Wi-Fi is carrying over half of all the mobile traffic coming off of devices, well over half actually, and they're forecasting that Wi-Fi is going to carry over half of all IP traffic globally, which is an even bigger thing. So we need more spectrum. The second reason is, for my share, the Wi-Fi gigabit brand promise is stalled. So just out of curiosity, how many people here run 40s or 20s as your default channel width? See? So as a manufacturer that ships 80 capable and now 160 capable products, right, to have my customers essentially defeaturing the product as soon as they take it out of the box is unacceptable to me, right? So, for all the obvious reasons. And the rates are only going to get faster, right? So for us to get to gigabit, just Shannon's law says you need more or less 80 megahertz with the technologies we have today. So, and if I've got DFS channels, right, that's a challenge for some clients, for some vendors, and so on. So we really want to make the 80s and the 160s viable. And then finally, 5 gigahertz is beginning to show strain, and again, you all have experience with that, and certain use cases are kind of the leading edge of the wave, right? But it is nonetheless the fact that it's increasingly common. And how many people have run into LAA yet in the field? Don't imagine too many. Okay, so LAA is starting to roll. We saw it at the Super Bowl this year outside Mercedes-Benz Stadium in kind of the public festival areas. It's starting to go into some other venues, and so we are going to have real competition in the band and in some areas that are already spectrum challenged. So anyway, we need more. So how much more do we need? So this has been studied by a couple different organizations. Qualcomm did an interesting study, and then the Wi-Fi Alliance did a study about 2 years ago. These studies, so just pay attention as I'm walking you through the story here, because for those of you that have interest, the steps that we're taking are typical steps that would occur for any band, right? So if I wanted to go open up a millimeter wave band, for example, or I wanted to go reallocate something below 900 megahertz or below, I would have to go through similar steps. I have to justify that I have a need, right, and how much spectrum is required for my application, right? I have to show that I can coexist safely with whoever's already there, or come up with a plan to, basically displace them and compensate them and so on. anyway, the Alliance looked at a couple different scenarios, but if you just look at the purple bars, the 2025 average and high, we're somewhere between 800 megahertz and about 1700 megahertz short. And then this is a chart from the new Cisco VNI, and you can see they do a nice job of breaking down mobile-only traffic, which is the gray box on top, meaning just basically cellular carried, and then the two in the middle are Wi-Fi based, and then the light blue in the bottom is still wired. But it's just remarkable how much Wi-Fi is carrying, and they project that this is actually going to increase in the 5G timeframe because the speeds are going to go up, but the way the speeds are carried is largely in unlicensed spectrum. Right? So we need about a gigahertz of spectrum, more or less, to keep up. So where do we find that in what is effectively the Malibu of spectrum, right? We talk about low bands, millimeter bands, mid-band. Each of them has propagation characteristics. So the low band below 1 gigahertz has, it's got really good penetration properties. That's why, the cellular networks use that spectrum to start with. But it's low bandwidth. On the high end, on millimeter, incredibly high bandwidth, but it has trouble getting through walls, right? So the mid-band has this great, has really nice penetration properties. But it's also got a good bandwidth, right? So it's a good mix, and of course it's awesome for indoor broadband. So if you just as kind of a filter, you say, okay, if we say 80 megahertz is kind of the unit of increment we're looking for, right? Where can we get a bunch of contiguous or nearly contiguous 80s, right? And the point of this slide is we didn't just pick 6 because it's next to 5, right? It's not how the process works. You've got to go do kind of a rigorous analysis. And so we looked at, we basically looked at everything between the current low Wi-Fi band in 2.4 and about 13 gigahertz, right? To say, okay, where can we go? What are the options available to us? And these dashed red boxes are essentially where you have blocks of in this case, 160s. So you have 160 on the left, 2 in the middle, 3 on the right. The black bars are DoD restricted bands in the US. And I think we can all agree from the DFS experience that if we can avoid DoD bands, it would be probably a helpful thing. So we're looking for bands that are not DoD restricted, but just because a band is not restricted does not mean it's not in use by DoD, and that's what the gray bars are. And if there's a DoD application, then the National Telecommunications Information Administration, which is basically the FCC for the federal government, they have a say, right? And so that's suboptimal for a bunch of different reasons, but it can be done. We've done it before. If any of you are following CBRS, so that's the kind of chunk in the middle. And part of the reason why the CBRS proceeding has dragged out so long is that the incumbent that they have to deal with is the US Navy, right? And they have the shipborne radars. And that figuring out how to mitigate against that incumbent has been a key problem. So then if you look at Europe, right, because we don't want just spectrum in one country, that doesn't ultimately help move the needle. There's also a lot of those same bands are in use by the European defense various entities. And then if you look at the cellular allocations, so 5G in particular, as I said before, a lot of the 3 gigahertz band has been designated, so 3.4 to 3.8, or really 3.3 to 3.8, has been designated at the last World Radio Conference for mobile telephony. And some countries, there's an open rulemaking in this country now from 3.7 to 4.2, and the UK also is looking at 3.8 to 4.2. So ultimately, most of the 3 gigahertz band will be dedicated to 5G in various countries. So that's not really an option. So then you look above the current Uni-4 band, and as I said, we go all the way up to 12.7, and conveniently there is this block of non-federal, non-restricted spectrum that happens to be adjacent to Uni-4 that potentially fits 8 160 megahertz channels. And that is the reason why we have sort of coalesced around the 6 gigahertz band here. And so it's also because of the way that the incumbents of the band, which we'll talk about in a minute, it's effectively globally harmonized, meaning that it's the same incumbents in every country. And we think that those incumbents are pretty easy to coexist with, and we can basically drop in what we call an underlay, right? An unlicensed underlay. And those incumbents can continue to grow their networks just fine, but because of differences in elevation and use cases and antennas and so on, we think that Wi-Fi can come into the band and coexist safely. So we did that study and kind of settled on 6, and then this is, just to give you a taste of kind of where we'll end up. So this is what is under study right now in the United States. Well, actually, there's an open rulemaking, and in fact, this last Friday was a key milestone because we had, that was the filing deadline. I'll walk you through the NPRM process here in a minute, but the filing deadline for the first phase in the process was Friday, and so all the filings have poured in now. So this is actively underway, but there are 59 20s, and sorry for the text goof on the left here, but 59 20 megahertz channels, 7 160 megahertz channels, and 14 80s, right? So this is an incredibly meaningful amount of spectrum. In Europe, not quite as much. There's a European Commission mandate to look at the lower 500 megahertz of the band, which again is still game-changing. So in either case, we're talking about more spectrum than we have today in 5 gigahertz, right? We have about 565 megahertz in the US. The UK is a little less, so about doubling the inventory in Europe, and basically more than tripling it here in the US. And most of the world follows either these two rules, right? There's some exceptions, but even countries like China, for example, typically follows EU rules insofar as frequency allocations are concerned. So who's in the band? There's no unallocated spectrum, as I said, especially in the mid-band because it's got these awesome properties. So let's start walking through some of the terminology that you're all going to be learning here over coming years. So let me start first with what are called services, and then we'll talk about who actually runs networks. But a service is a specific term. Services is it's a statutorily defined service that is determined by regulators. It's basically what the rules are around particular communication services. So for example, we operate under what's called Part 15, right, which is the unlicensed band, or licensed by rule. But there's also something called the fixed service, right, which is basically point-to-point microwave. And as you can see in the picture, there's a thing called the mobile service, and so that's for anything that is obviously not fixed. So there'd be things like news trucks and helicopters, that type of thing. Then there's the fixed satellite service, and that exists in a number of different bands and in different directions. So there's the space to Earth and then Earth to space directions. And then a lot of you probably have Sirius XM in your car, so there's a thing called the satellite digital audio service. And so each of these has, if you look at the Code of Federal Regulations, they all have a particular part. So we're Part 15, the fixed service is Part 101, the broadcast is Part 74, Part 78, and so on. And these are all literally they have the force of law, right, that stipulate all the different requirements. In terms of then who uses those services, you have operators, right? So we would be an operator, all of you would be operators within the Part 15 service. But in this case, in the 6 gigahertz band today, the dominant operators, first of all, the single biggest category is common carrier. So the picture on the left, it's kind of hard to see, it's on a mountaintop, but this is the original long haul band for the wireline carriers, right? AT&T, Verizon, and so on. And there are about 100,000 of these links in the continental United States. I'll show you a map in a minute. Verizon alone has about 40% of the links within this category. AT&T has about 30% of the links. And the category as a whole is about 40,000 of the 100,000 links. So very important incumbent. Then we have various kinds of business users. So those are the MG is the code that the FCC uses for these. So utilities and railroads would be examples of this. Financial services as well. There's a bunch of privately owned microwave networks from Chicago to New York that are used by the high frequency trading community, which is how they front run the market. Basically, they arbitrage the latency differences between air and glass in the fiber. So those are examples of private sector users. And then in the Uni 6 and Uni 8 bands are public safety and electronic news gathering. And and that applies to both airborne operations as well as ground operations. And another thing about the band, so Uni 5, just kind of moving from left to right, Uni 5 and Uni 7 are exclusively fixed bands, so you will not find anything mobile in them. Uni 6 is an exclusively mobile band. You won't find anything fixed. And then Uni 8 is kind of a mix of both of them, if you will. And I'll show you another breakdown of that. So these are all the people we're going to get used to, right? So we've been worried about radar, right, for a lot of years. These are kind of the new our new roommates, if you will, assuming that we get a favorable decision. So I'll just give you a little bit more background information, and we're not going to deep dive on any of these. I'm just trying to give you a quick level set today. But the first is the fixed satellite service, and this is it's fixed because it's basically in geosynchronous or geostationary orbit. Those are two different things, if you're not aware. So for the geosynchronous, the geostationary satellites, they all exist in this thing called the geo arc, which is basically at the equator, plus or minus a couple degrees. And so there's this band that's been set up, and they have beams of varying sizes, right? Just very similar to what if you're deciding between an Omni and a Patch and a Yagi, right? It's the same kind of idea here. So they have really wide hemispheric beams that go from basically pole to pole. They have continent-sized beams, so they can just light up a country, which is what you see here. And they have pinpoint beams that'll light up just like a region, like New England or Northern Europe, something along that line. And of course, just as as you're familiar with other antennas, the tighter the beam, right? I get rejection off the side, but the gain is increased in the center of the beam, and so they have different properties from an interference perspective. And the issue here for us is they're worried about aggregate interference, right? If you have a billion or a couple billion Wi-Fi devices suddenly show up in this band, right? Even though they're individually we're transmitting, very irregularly, right? Wi-Fi doesn't use much airtime normally, and we don't have that much power. But if you think about billions of devices over a landmass the size of the continental United States, that starts to actually add up. So we had to study it. Here's a map. The slides will be available after the talk, but this is a map that Boeing maintains of all the satellites in orbit. They're about every 2 degrees around the geo arc. So there's a segment of these that had to be studied. And we actually simulated the effect of a billion Wi-Fi devices on this constellation. Moving on to the fixed service, we have, this is the United States, and I'll show you a chart for Europe. This is looking at the lower 6 band, which is basically runs from 5925 to 6425, and then the upper 6, which is 6425 to 7125. And combined between the two, as I said before, it's about 100,000 of these links in the country, and they're all over. They're in metro areas. They're also in kind of in the middle of nowhere. They're rural and areas interconnecting states, because, as I said, this is the original long haul networks, right? And a lot of this has been displaced by fiber. Some of these are backup circuits now for the fiber that's primary. But there are a lot of places, we heard, the utility industry has filed pretty loudly in opposition in the proceeding, and they talk about, power plants that are, in the middle of nowhere where, AT&T or Verizon just never, or whoever the local provider is, there's no economic reason to pull fiber to that location, right? So they use microwave for that purpose. So it's a very heavily deployed band, and these are all critical services, as you can tell. In Europe, it's about 8 times less densely deployed in the US. We've identified about 27,000 links in Europe. and it depends significantly on the country as well. This is just a picture of some of the links in France. They have quite a different kind of geometry to them. But again, we're having to study, we're having to go country by country basically and identify the assets if this information is even available. So France has this website where you can do this, and so does the UK, but Germany does not. Norway does not, right? So it's very difficult to actually acquire this information. One other view of the band, and this will give you some idea why the Uni 5, 6, 7, and 8 breaks are where they are. So this is a different view. This is basically a view of who the incumbents are by the frequency component. So the colors, the y-axis is the number of links per megahertz, right? So we've just kind of normalized it because links have different sizes. They go from 400 kilohertz all the way up to 60 megahertz in bandwidth. So this is just as you go across the band from 5925 to 7125, for each 1 megahertz increment, how many links are in the ULS database at that particular spot. And you can see that in what effectively is the Uni 5 and Uni 7 bands, you've got public safety fixed, industrial, business, and then the common carrier. So remember I said common carriers are 40% or so of the total link population. And then in Uni 6 and Uni 8, it's dominated by broadcast and some public safety, mostly mobile public safety. So the reason for the breaks is that we want to tailor the rules to the incumbents in those particular subbands, right? We don't want to over-regulate or under-regulate, and we have to make sure that each of those incumbents is protected, but I don't want to take a rule that I don't need, right, and apply it somewhere where it might restrict spectrum access. And then the last concept, and this will kind of tee up the AFC discussion later, but what happens today, if so just forget Wi-Fi for a minute. Let's say I want to put up a new point-to-point microwave link. What do I have to do in order to turn that link on? Well, I have to go through what's called a coordination process, which is mandated in the Part 101 in the Code of Federal Regulations. And if I want to cite a 6 gigahertz transmitter anywhere in what's called a keyhole in front of an existing receiver, then I have to go through the coordination process. And the way that works is there's a bunch of companies that do this, and they have their own databases, and then they basically map out where my links would be, and they study the impact. They simulate basically the received power at all the other receivers that are within the keyhole. And so the keyhole shape that's defined in statute is on the left, but on the right is two keyholes from two ends of an existing link overlaid on each other and scaled to the actual distance. And you can see that one link takes out LA and San Diego, right? The whole corridor, right? The way the statute is defined. Now, part of the reason the keyholes are that big is that these are very powerful antennas. The median gain in this band is 38 dBi. And the link power, the EIRP is on the order of 65, 70 dBm combined. So these things can throw really far. And of course, the keyhole shape is going to be quite different for a Wi-Fi device. But nonetheless, this is how it works today. So if we want to come in the band, we have to basically coordinate with these devices. But the challenge is, how do we do that for Wi-Fi equipment when we're shipping, as an industry, we shipped 3 billion chipsets in 2017. And so we need a process that's automatic and that can really scale up. So a couple of coexistence challenges with the fixed service. So we looked at detection, and one of the problems with detection is that first of all, the channelizations don't line up. And so what I'm showing here is this is the Uni 5 band, so 5925 on the left, 6425 on the right, so we kind of zoomed in now. And I'm showing two of the two most common FS channelizations, so 10 megahertz and 30 megahertz. And these are on the order of 80% or more of the links in the band. So first of all, the channelizations do not line up in any meaningful way. So from a detection perspective, it's challenging to design something that can definitively do that, although it's possible. But the other problem is that these links are virtually all FDD. So that's the red and the blue. So I could be parked under a tower, right? And I can hear the transmitting side, but I can't hear the receiving side. And they are paired, so in theory there's a known relationship between the two. But in studying this, there are enough scenarios where if you're in the middle or if there's a funny geometry, you could hear one but not the other, and we could potentially be transmitting where we shouldn't be. So that's kind of one challenge that we had to work through, and this is part of what got us to the AFC type of solution. And then the next challenge is, while a lot of these links are in rural areas, there are a lot of these links in metro areas, and in particular some of the really dense metros. And this is actually, these are cut from an opposition filing in the record, and their point here is that there are a lot of tall buildings that poke into the beam width of some of these links. And so what they're showing here is a receiver up in Queens that is aiming at a transmitter that's in lower Manhattan, right? And that beam happens to cut through, as you can see on the right, a number of different buildings. And they argue that they provided link budgets and said, oh my God, this can never work, right? So these are the kind of things that we have to come up with rules that will make the incumbents comfortable that we're addressing this sort of situation and not causing a threat to their links. Okay, so that's kind of setting the stage. Now, let's talk about the regulatory process, and then I'll talk to you a little bit about the study, and we'll close by talking about AFC. So we are really encouraged. We do feel like the proceeding is going particularly well, especially here in the US. It seems like the Congress has been very supportive, so there is a whole advocacy component, and a lot of people here know me. I haven't spoken here in a couple of years, but you all know me as an engineer. I'm not accustomed to doing policy work, but one of the awesome things about coming together with Hewlett-Packard Enterprise was HPE has a really excellent government relations capability, not just in the US, but elsewhere. And so that's enabled Aruba to really kind of step forward. I mean, in the past, it's been just a couple of really big companies that have kind of done this work. But we were able to kind of step forward and really roll up our sleeves and get deeply involved. And then other companies are with us. We built a coalition of 11 companies. We have Apple, Google, Facebook, Microsoft, all the big silicon vendors, Qualcomm, Broadcom, Cisco, and Ruckus are with us. Because these kinds of things, it really takes a village, right? The FCC is not going to allocate spectrum for one technology or one company, unless, of course, you're paying for it at auction. So Chairman Pai, 2 months ago, made a public statement that he'd like to see a favorable decision on this this year, which would be great, but obviously we have a lot of work to do. But both the majority and minority sides of the House and the Senate have been very active and very supportive on this. They've sent letters to the Commission on our behalf. Wi-Fi is like a totally bipartisan issue, which is great. And so where we are now is in the FCC in the US, the process that you follow, there's a couple ways that you can get a rulemaking started. You can file a petition, which we ended up not having to do here, which was great. The goal of a petition is to get a notice of inquiry, which is where the Commission basically, for those of you that do bids, right, you can think of it like an RFI as opposed to an RFP. And in this case, the FCC went straight to an NOI, which was completed in 2017, and that generated a lot of contributions from both sides. And then most of last year was spent advocating to get the NPRM issued, which they did towards Thanksgiving of last year. And then it was adopted formally in December, just before the shutdown. And that started a 60-day shot clock for filings. And that is the deadline that expired this past Friday. So basically, everybody gets kind of a first pass to kind of lay down their positions, put technical data into the record, and so on. And then a new shot clock has started. So there's a 30-day reply shot clock. So everybody gets to file their rebuttals, right, to what other people said in the first round. And that currently is 30 days. We're hoping for an extension, but that deadline is March 18th. And then most of the rest of this year will be all of us going into the commission and kind of arguing our case in person, and then working with each other. So we are working with the common carriers, we're working with the utility industry, we're working with the public safety community on the mitigation proposals to try to get them comfortable, and we've already made changes to our positions on this. So, but we're moving very expeditiously for a proceeding of this scale and scope. We are moving extremely fast, and we'll see. I don't want to jinx anything, but again, hopefully, as you're getting a sense, there is just a ton of work here. So the timeline in the U.S. So the STAR is where we are now. We're just before. We're in this last round of the NPRM, the formal stage, and you can see kind of some of the steps that we've been through already. So we've been at this for about 2.5 years. Some companies even longer. Some of the silicon companies, and then also, if you haven't heard, the 11AX. Standard was revised to go up to 7125, so AX will be ready even in wave 1 will contain provisions. You can't buy it, but it's 6 gig ready, and then product actually would hit. So let's say there's a report and order, conservatively in the first half of next year, then we'd be looking. Basically, our goal as industry is to catch the second wave of AX. And those would be the first products that would ship that would be sort of 6 gigahertz capable with whatever spectrum we're given according to whatever rules ultimately are part of the rulemaking. And by the way, as you saw in this last slide, right, reports and orders can be changed and challenged, right? So that's part of what's happening in the CBRS band. There have been 4, I think maybe now 5 reports and orders in that proceeding, including the most recent one where the cellular industry came back and challenged the rules again. So just because you get it doesn't mean that that's the end of the line. There can be litigation, there can be all kinds of drama. But anyway, we're hopeful that we will be able to ship some new 6 gig capable channels in the late 20, early 21 timeframe, which is, if you think about it, I mean, about 2 years from now, the AX Wave 1 products are just beginning to ship. Right, so that's actually even fast compared to kind of the historical run rate for WFA. In Europe, it's really much more complicated. So first of all, the European Union is 28 countries currently, and then beyond the EU. There are another 20 countries, so a total of 48 countries in what's called CEPT, which is the European Conference of Postal and Telegraph Administrations, and they basically have harmonized the rules because you have a lot of adjoining countries and radio crosses borders. So they have agreed on basically the rules for different bands. And so if you want to make a big change like this, they all have to kind of come together. So we're working through a process, and in Europe, as it's a complicated beast. So these are all different groups that have some role to play in the process. The European Commission started it with the mandate, and then it went to this thing called the ECC, the European Communications Commission, which is currently studying it. So they're acting on the mandate. And then eventually we go over to ETSI, which is where the standards get created that determine, okay, what do we as manufacturers have to comply with, and what are the rules that govern the ban? And so it's very complex. And so in Europe, we spent the year doing a study. So there's a 200-page report that's been compiled with very detailed technical studies from different administrations and from, we put in a significant amount of content, but we have a much longer path in Europe because of all of these steps that go in. And so there's a series of 2 reports. Report A basically has to do with the feasibility. Can 6 gigahertz be shared with unlicensed equipment or not? And then report B is basically what the rules are. What mitigations, this is the term of art that we use, would be required for an unlicensed system to coexist in the band. And then those two reports collectively are the foundation on which the rules and the statutes are drafted. So we're looking realistically, 2021 would be the earliest date at which there would be a political decision to open the band, and product would then follow that. So it's a ton of work. So here's what's in the US NPRM. So basically what was proposed, and this is a little different from what we advocated in the NOI stage, but they basically proposed 3 classes of devices. So the orange bubbles are standard power APs, and you can see the Uni 5, 6, 7, 8 breakdown. And those have been proposed at basically 4 watts. So the Uni 3 power levels with AFC, so with database control. Is what's in the document today. So every AP in that band, whether indoors or outdoors, would have to be controlled by a database if what's in the text of the NPRM today was adopted tomorrow. And then in the Uni 6 and Uni 8 band, they took our proposal for what we call low power indoor. So these are indoor only devices. They cannot go outdoors. They're lower power, so 1 watt. So think DFS channel kind of power, right? So power levels you're using today, but we wouldn't have outdoor channels in those bands. And then client devices, they propose to cap at 18 dBm across the board, which is obviously a problem because now we have asymmetric power between the access point and the clients in a bunch of situations. So there's a lot of what we advocated for in here, but there are some really important things that are not. In particular, we said, we've argued since the beginning that low power indoor should exist across the whole band. It should be possible for indoor devices to, again, because now that you're familiar with the incumbents, right, they're all outdoors, they're at height, right? The median height of an FS antenna in this country is 43 meters. So the geometries of the two systems, right, are very different. Wi-Fi devices exist almost exclusively below 10 meters. Right, except in some tall buildings. So this is great. We're very appreciative of the commission for making this step, but it doesn't move the needle for us. And in particular, it causes some challenges to us as a manufacturer. So just one of the practical problems, and if you go look at the filing, so we talked about this in our filing on Friday. So this is what the band looks like from our perspective for the next 2 to 4 years from the day that the commission votes to open the band. The red crossed out channels are ones that are AFC. And the reason they're crossed out is that it takes time to work out the rules for a database band, right? If you think about TV white spaces, if you think about, the original CBRS report and order was over 6 years ago, right? And we're still not shipping product. So the only spectrum we'd be able to use out of the gate would be the low power indoor bands, right? And because of where the breaks are, this is what's effectively usable. In the top is what's with the currently approved IEEE channel plan. And in the bottom is if we shifted the channel plan right by 10 megahertz. But you can see that right now we don't even have an 80 in Uni 6. And so it really creates a question there. So do I ship product that's capable of using the whole band, that's future-proof, if I know that it's going to be at least a full generation until I can use some of those other channels, or do I ship a product that's got maybe it's only enabled for Uni 6 and Uni 8, right? And then different countries are going to do different things, so we get a harmonization issue. So it's really problematic for us. So this is what we counter-proposed with, and we'll see what happens. So basically we said, okay, fine, standard power, we agree, except we think that we can do standard power safely in the lower 100 megahertz of Uni 8, and low power indoor across the board, it's perfectly safe, and we'll show you how. And then we introduced a new class of device that we're calling the very low power AP, and you could think a tethered mobile phone would be sort of the dominant use case here, or maybe short range applications between a gaming console and a controller, that type of thing. And then we said for clients that they should be able to match the power of the AP to which they're connected, and a TPC should be mandatory, right? So this is the position we've taken in the record pretty aggressively. We're going to be fighting for everybody to try to get as close to this as we can. But obviously, we're up against some pretty powerful interests. I think in the interest of time, I'll leave. So I've got a couple of slides in just terms of how what the logic is in terms of whether you have to coordinate or not. But I want to just get to the sharing study and then talk about database. So again, this is going to be a little head spinning for some of you, but again, just to give you a sense of peek behind the curtain, right? What does it take to do one of these things? So the slides I'm going to show you here, just a couple of them, are basically from what we showed the commission and we showed Incumbents. So we produced a study. We spent all of 2017 working on it, our 11 companies, at no small expense. And the report found we simulated basically 1 billion Wi-Fi devices in the continental United States against the existing fixed service population, and also we looked at the satellites, and we modeled the interference, right? What if you throw 1 billion Wi-Fi devices at that population, what happens? And what we found, we didn't really know necessarily what was going to come out of this, is that in the base case, like we just said, okay, let's take the uni rules in 5 gigahertz, let's just start with those. What does that leave us with in 6 gigahertz, right? And the idea is how much more work do we have to do on top of those rules to exist safely? So again, we simulated, we randomly dropped 1 billion Wi-Fi devices thousands of times in a computer. And we had 3 basic findings. So relative to the fixed satellite service, the interference is below minus 21 I over N. For those maybe less versed radio heads in the room, that means 22 dB below the noise floor from the perspective of the satellite. And this I over N metric is how interference studies are done. And the standard we're trying to meet there is at least 10 to 13 dB. So we have a lot of excess margin there. And in fact, it turns out that the existing, again, fixed satellite and fixed serve and point-to-point are already coexisting. So we actually did a second study. We just said, okay, how much interference are the satellites getting now from the fixed links that are on the ground today? And it turns out Wi-Fi is 40 times, the energy from 1 billion Wi-Fi devices is 40 times less in absolute terms than they're already getting painted with from the point-to-point microwave guys. The second finding is that with respect to so that was satellite. With respect to the fixed service, the point-to-point microwave, we found that 99.8% of the receivers had aggregate interference levels below minus 6 I over N, and that's the operative threshold here. Minus 6 is equivalent because power adds, right? You know, if you take 2 radio chains, right? If I have a 18 dBm chain and an 18 dBm chain, the combined power is 21 plus 3. So an I minus 6 is equivalent to increasing the combined power by 1 dB. So that would be taking 1 dB away from their noise floor. And we found that 99.8% of the time that was not the case. But then we also said, okay, for those links that saw a slight increase, did it have any effect? And that's the key thing. Like, interference is allowed under all the rules, but it can't be harmful interference, right? And so there's an argument over what constitutes harm. In this case, we said, okay, these links are designed to specific criteria. They're 5 nines or they're 6 nines, right? Which we throw those words around, but in the microwave community, those terms have very specific meanings, and there are internationally defined calculation methods that tell you that you meet the 5 nines or the 6 nines targets. And so we found that for those links that did experience some interference, that there was no change, 0 change in their availability relative to their design targets. So again, we contend that even though there might be a little bit of transitory interference, and it would be foolish to argue otherwise, right? Certainly there are going to be geometries where there's some detectable energy, but that it is not harmful. And that's part of the debate that we're having in this process. And then with respect to the mobile service, which is different, right? So that can, the TV news truck, right, with the pop-up antenna, right? So that's what's in this band. That could set up outside this hotel, right? If something happened, or what have you. So we looked at those. Those are mostly one-way links going back to a tower on top of a building, right, or co-located with a transmit tower. And 99% of the time, we didn't degrade those links. What's interesting about the mobile service is that most of the time, they already have problems. So if you're the driver of one of those trucks, right, and you need to set up for a shot, right, you don't know what's going to be around you. You've got buildings and trees and whatever. So they already kind of have this process where they fiddle with the truck to get a clean shot at the tower. And in those cases where we did have an effect, we believe that existing practices in that community they're not even going to notice it. So we studied, as I said, 1 billion Wi-Fi devices. So we had to come up with a model based on the US Census data population. We got to 958 million devices. Not all of them are transmitting at the same time or on the same channel. So we said, okay, we're going to look at the busy hour, which is when people are home. So that's basically 7 to 8 p.m. Pacific time. That's the maximum window. That's when all the busy hours of all the time zones line up. So if I'm the satellite up here, that's when I'm going to see the most noise. And then we had to come up with, okay, how often are devices transmitting? Well, we said, let's say every man, woman, and child in the United States is watching Netflix in the busy hour, right? So that's 5 megabits per second. And by the way, you've got 9 other IoT devices for every high-speed cellular device. So that got us to 400,000 instantaneous transmitters at any instant microsecond of time. And then we distributed those devices based on US census population, right? So suburban, rural, and so on. Then we had to come up with a power model, right? Because we're simulating interference from all those devices to all of the receivers. And then finally, we had to come up with a transmitter with a height model. And what we found, and this is just, when I say random drop, this is from the European study we did, but basically this is a view of a 150 kilometer radius from a fixed receiver in downtown London. And the blue dots on the right are where the simulator dropped all of the RLANs in that area. And they dropped, for this particular run, there were almost over 22,000 RLAN devices within that 150 kilometer radius. And then what we do is we basically sum up all the interference from all those devices at each of those receivers. And this is the head spinning part. So for those of you, the statistics fans, if you know CDFs, right, this is just the distribution of all the interference, basically every geometry between every Wi-Fi device and every fixed receiver. This is the sum of all of those power level, and the x-axis is the I over N. And what you see is that overwhelmingly, we are to the left of the -6 or 0 threshold. So we argue that we can safely coexist. But this is the kind of work that you have to do. Every band that gets open has a sharing study of some kind like this. Again, it's done for millimeter, it was done for CBRS, it's done for white space, it's done this. The cellular guys don't have to do it necessarily because they clear the band, right? And it gets licensed. But this is not inexpensive to do, and that's why you have a lot of companies working together on it. So the last part of the talk here is just a quick primer on what you can expect around automatic frequency coordination. So this will be enforced on all standard power access points. The goal is to ensure that a device does not transmit on a channel and in a place that would create harmful interference to a fixed service receiver, which means that I have to know my location, right, very accurately. And that can be done a whole bunch of different ways, but that's a new requirement for us, right? Except for some outdoor equipment, we don't normally care about that historically. And then the device will communicate with the database or AFC. It'll say, I'm here, I have these transmit characteristics, I want to use this EIRP, maybe I have this antenna characteristic and so on. And the AFC will respond with usable frequencies in that location from which I can then choose. And how I determine my location, what we've said to the commission is, don't tell us how to do this, right? We're 20 years in from the last ruling. There was no iPhone for, 5 years after the final 5 gigahertz order, right? We don't know what technology we're gonna have 20 years from now. So just tell us what we have to meet. What are the criteria, or what, the phrase we used was ends oriented, and then let industry figure out the solution. And also, if you think about the Wi-Fi industry, right, we have such incredible diversity of price points and business models, right? And it's only getting more diverse as time goes on. So we don't want to foreclose, right? We want to take all the richness that's in 5 gigahertz and make it possible to come to 6. So we don't want the regulation to be heavy-handed. So specifically with location, we don't want to say, okay, you must do GPS, right? GPS is expensive, right? It's energy consuming and so on. Some devices don't need it. So if I can do it another way, right? Maybe the ISP, right? So Comcast, Charter, AT&T, whoever, maybe they can provision it, if it's installed, right? And the data sits in a system. Could be a smartphone app, right? That securely talks to the device when you're setting it up, right? And it pulls the lat long off the phone. Whatever, right? As long as the manufacturer can show in the certification process that it meets the location accuracy requirement. And then the way it'll work is you'll have standalone devices, which are what I'm showing up top, and then managed networks with multiple APs down in the bottom. They'll either sense their location, that's the little antenna hanging off the side, or it'll be stored, right? It'll be provisioned by a professional installer or in an OSS system, and then they will periodically communicate with the AFC, and there'll be some mandatory interval, minimum time recheck period, at which they'll go and update, has anything changed? Is there a new FS, right? Is something different in my area? And we're proposing to use the ULS, which is the FCC's universal database, as the sort of source of truth for this. So unlike in some other bands that have databases, we don't see a need for the AFC to synchronize with each other, which is going to help us get to market a lot faster. And then almost done here, so this is kind of the key concept. So this is a 2D chart, but the proposal, pretty much everybody has agreed, even the incumbents have agreed, that we should use 3D protection contours. So just imagine a shape kind of in the, just take if you think of a Yagi pattern in your head, but even tighter, right? These beams are about 1.8 degrees or less, right? Just stretch that out. So there'll be an area in front and around of each of these FS receivers that, depending on the characteristics of that particular antenna, will be blocked from use. And of course, because it's all relative, right? The size of that area depends on what the power of the Wi-Fi device is. If I'm transmitting with less power, then I've got a smaller exclusion zone, right? If I'm trying to use more power, I have a larger exclusion zone. So we independently calculate the position of the RLAN device that is asking for permission, plus some uncertainty because GPS is not perfect, and also the APs are going to protect their clients. So unlike in white space where the clients have to be individually admitted to the band, in this case, we want the AP to do the work. We want no extra burden on the clients, right? So I have to take some extra buffer around the AP. And basically the the light green circle cannot touch the red area. If it does, then that spectrum in that area would be blocked, right? And that operating frequency. And you just repeat that for all the incumbents in an area, and that gets you to, I'll just skip over this. Just go to the final picture. So this is my last slide. This is just kind of a prototyper that we have going now. So this is a view of the San Francisco Bay Area showing fixed service receivers. There's a couple hundred FS links in the Bay Area. And you can see the call signs on the right side with different channelizations. And even, so the crosshairs are up in the mountain here at an area that has a view back to the Bay Area. And you can see what that does to spectrum availability on the bottom. So we've got 20s and 40s, but with the particular set of inputs we use for this chart, which are very conservative, but this is a real possible outcome, we don't have any 80s in this location. So that's another thing to sort of wrap your head around, is just because we have the whole range, or at least in the AFC bands, you might not have all of the spectrum in every location at every time. And so again, the AFC system will manage that, and it will work with the radio resource algorithms from the different vendors to manage it. But anyway, so I hope that was useful. Again, it's nothing you need to do today on this. We're fighting the battle for you, but I'm very hopeful that we'll be able to actually be talking about products and rollout timeframes in about 6 quarters with you. And just cross your fingers and wish us good luck here.